Thanks for selecting this video. My name is Donald Wortzman. For those that don't know me, I recently published two books. One, The Doors of Ishtar thriller, and the other, The Gyroverse, a book on original physics theory. Now I want to speak on a watershed event in the direction of physics. On the completion of Einstein's theory of relativity in 1916, Einstein predicted that starlight passing in close proximity to the sun would bend towards it. Others, including Newton himself using non-relativistic ideas, had previously predicted that light would be bent by the sun. But Einstein predicted that it would bend twice as much. In addition, Einstein also claimed that to test this hypothesis, there would have to be a total eclipse of the sun, so that the sun's brightness would not overwhelm starlight. The test was scheduled for 1919, the year of the next total solar eclipse. The tension built because this was a challenge by Einstein against the greatest physics mind ever, Newton. In fact, once Einstein was proven right, the result captured the imagination of the public, hitting the front page of all major newspapers and catapulting Einstein to rock star status. Einstein attributed this doubling of the bending to general relativity's contention that matter curves space. The non-relativistic calculation for gravitational bending has taken two tacks. Some treat light as a particle and others treat light as a wave. However, both result in exactly half the actual bending. Because light doesn't generally show its particle and wave properties simultaneously, conventional wisdom presumed that both were just different ways of performing the same calculation. The gyroverse takes a slightly different tack. It uses both a particle and a quasi-wave procedure that clearly illustrates that both calculations are not equivalent. Although they cause an equal amount of bending, they have a different bending profile. The particle procedure results in the bending being maximum where the light beam just skims the sun, dropping off greatly at either side. On the other hand, the quasi-wave procedure shows that the bending is zero at the point of tangency, but is much greater off to each side. This shows plainly that both components are not just different ways of making the same calculation, but describe completely different mechanisms, which can be shown with the help of the following illustration. Here is the illustration. In this illustration, there are three figures. The bottom one depicts a photon stream coming from a far-off star, grazing the sun and heading towards Earth. The force of gravity is shown by the force F pulling the photons along the little r vector towards the center of Earth. The amount of bending is exaggerated in this illustration, but is only about 2 arc seconds. Remember that it takes 60 arc seconds to make an arc minute and 60 arc minutes to obtain 1 degree of bending. Also notice that theta is the angle that the gravitational force makes with the vertical. To compute the total bending, the gravitational force is broken into its two components. Each component causes the photon stream to bend a little. The vertical component, shown at the top left figure, works best by treating the photons as particles. The vertical force is F times the cosine theta, which is maximized where the photon stream just grazes the sun. But its force falls off rapidly to either side of the distance, as little r gets bigger, but also because cosine theta gets smaller. The figure at the top right depicts the horizontal force component. As suggested by the wavefront, it emphasizes the photon's wave-like structure. This force, F times the sine of theta, also falls off as little r gets bigger, but stays larger than the vertical force as theta gets much bigger. In effect, this component is zero when the vertical component is biggest and maximum off to the side and falls off much slower. Each of these force components lead to the same amount of total bending, but have a very different bending profile. Combined, they make the same total bending prediction as general relativity. But most importantly, curvature of space is not necessary to explain it, or in fact, anything else. Thanks for watching. This is Donald Wortzman signing off.